the invitation. I realize, of course, this is I'm a little bit of an outsider to this group, you know, which mostly earth scientists and the like, and so I'm actually very much looking forward to your reaction and to this conversation today, because for us as economists, we are of course tasked to think about the economic impact of climate change and the economic impact of global warming, and we're quite comfortable modeling the economic side of things, but we of course have a lot to learn about the climate side, and so in that sense I very much look forward to our conversation today. This paper is part of a collaboration of a group of economists and a group of climate scientists. So hopefully, although I'm an economist, I'm not going to say anything too outrageous. But anyway, I'm very much looking forward to your reaction and your comments. So what we're going to do in this paper is we're going to try to evaluate the economic costs of coastal flooding, and so how will we go about doing so? So of course, you all know that the rise in the sea level is going to be one of the world's major challenges in the next century or the next centuries. So global warming it leads to the thermal expansion of oceans, leads to the melting of glaciers, the retreat of ice sheets in Greenland and Antarctica, and all of this together raises the sea level. And according to the IPCC, if you take a sort of middle of the road emissions scenario, the expectation is that the global mean sea level will rise by about 0.3 to 0.6 meters by the year 2100. Now, how do economists go about quantifying the effects of sea level rise? So we would argue that very often they take a fairly naive approach, and by that I mean they essentially do an accounting exercise where they say, okay, these lands or these pieces of land will be flooded, say in 2050 or in 2100. Let's compute or let's estimate the value of structures or the value of GDP that is currently being produced on those pieces of land, and let's call that the cost of coastal flooding. So it's essentially just saying whatever gets flooded, let's calculate the economic value that is being produced in the areas that get flooded, and that's what I'm going to call the cost of rising sea levels. So what is of course lacking in that naive analysis is the fact that humans will of course respond to sea level rise, and will respond to coastal flooding, for instance, by moving, right, or by migrating. And so you'll have certain clusters, say, of economic activity, maybe some cities or parts of cities that get destroyed, but then as economic activity and people move elsewhere, new clusters of economic activity and new production centers will emerge elsewhere. And so you have to think about how the whole economic geography of the world is going to be reorganized as a consequence of climate change. And it's in that sense that we argue in this paper that we kind of need a change of focus from just simply computing the value of lost economic activity in the areas that, for example, might be flooded, to a more comprehensive analysis where we think about the entire change in the economic geography in the location of economic activity. And of course, for that, we need a high resolution dynamic model that encompasses the entire globe, right? And that's kind of where we come in. We've been developing these kinds of economic models. I'll give you a little bit of a taste of how these models work, and then we'll take a sort of a spatial dynamic model of the world economy, and then we will incorporate into that model the effect of coastal flooding or the effect of sea level rise. That's the exercise we want to entertain. And as I said, the main idea is to really think about how the world's economic geography is going to change as a consequence, in general, of global warming, but in this particular paper, as a consequence of sea level rise. So, in terms of the model, here are sort of the key features. Think of a world that we're going to split up into many grid cells, into many locations. In fact, we're going to split up the world in the quantitative exercise into 64,800 1 degree by 1 degree cells. Each of these cells or each of these locations will be characterized by 3 features. One is the location will have a certain amount of amenities. In economics, we talk about amenities as features of a location that make a location either attractive or not attractive as a place to live. So for instance, if I have a nice view of a mountain, well, then that would be positive amenity. If I have terrible humidity in summer and a really bad climate, that would be a negative amenity. So places are more attractive or less attractive in terms of living. Each location will also have a level of productivity that makes certain places more attractive to work, right? If it's more productive. Productivity, by the way, is going to evolve over time as the economy innovates and grows. And then the last characteristic of a location is its geographic position relative to everyone else. What we mean by that is, if I take a location, say, in the middle of nowhere, versus a location that's very well connected to the rest of the world economy, well, that second location will, of course, be more attractive because it's more connected to the world market. Then each location will have economic activity, will have firms, etc., that operate there. These firms will produce, but they will also innovate. They'll invest in innovation. Innovation will make the economy grow. And these places and these firms can trade with each other. Of course, trade is costly. There's going to be transportation costs, etc. Okay, and then lastly, and that's very important here, is that there's a certain distribution of people across the globe, and these people have some capacity to move, right? So in this model, adaptation through moving will be a very important feature. Now, of course, what's very important here and what's key is that we should be able to carefully measure and estimate the cost of moving, right? So just to run ahead a little bit, if you take a very simplistic view of things and you say, oh, people can just freely move, there's no problem. If you eliminate all costs of moving, then you could even argue that the whole issue of coastal flooding is not a very big deal because people can just easily move, right? Now, if moving is very, very costly, then suddenly the cost of coastal flooding would be a lot higher. And so getting those numbers right in terms of the cost of moving is going to be important in this framework. Okay, so what forces are present in this dynamic spatial model? One thing is we will be emphasizing the fact that economic activity is not equally spread across the globe, right? You have certain clusters that emerge, like cities with millions of people, high productivity centers, etc. And so how do these clusters come into being? Well, for two reasons. On the one hand, locations that have more people, that have higher density, those locations innovate more because they have a stronger local market. And then vice versa, because they innovate more and because they're more attractive and more productive, they will also attract more people, right? And so there's some kind of reinforcing or self-enforcing argument here, where high density places innovate more, and because they innovate more, they attract more people, and because they attract more people, they become larger and they become more dense. And that's kind of the economic geography, where you get clusters of economic activity emerging in different locations. Now, of course, there's also going to be some forces that limit the endless expansion of cities, and those are costs related to congestion on the one hand, but also other types of centrifugal forces that have to do with people's locational preferences, right? So fortunately, not everybody wants to live in the same place, right? People have different preferences, and that's another reason why not everyone in the world is going to end up living in the same place, right? And so think of a model like that with many locations, with clusters of economic activity that emerge and that maybe disappear over time. And then we introduce into that sea level rise. And so we're going to take a relatively simplistic view of what sea level rise does. We want to say that sea level rise destroys productive land. Simply, it's going to say that certain pieces of land which were previously used for productive purposes will no longer be available for productive purposes. And when that happens, although we don't have physical structures in the model, we do have all the cumulative past investments in technology in that location. But all those past cumulative investments are actually going to be lost, right? And so think about, say, Manhattan, or think about certain parts of Miami. These are very highly productive places. If those places are no longer available for productive purposes because of sea level rise, it's not simply the buildings that are going to disappear, it's the entire productive capacity that has been built up in these locations that are going to disappear, right? One other thing I want to emphasize is, when we talk about sea level rise in the context of this paper, we will be talking exclusively about permanent inundation, right? So there's, of course, a lot of interesting work to be done in the realm of sort of intermittent flooding, storm surges, etc. Here we're looking at sort of the sea level rise that will permanently inundate certain parts of land, and we're going to try to understand how that affects the global economy. So that's kind of the idea, sort of briefly laying out how the model works. We're of course going to quantify this model. As I said, we discretize the world into these 64,800 1 degree by 1 degree cells. We're going to have data on bilateral trade costs, on population, on output, on well-being for all of these cells. From the model, we will recover the level of productivity and the level of amenities of all these places. And then we have a methodology built into the model that allows us to identify the bilateral moving costs between different cells. And as I said, that is really key, right? Because the world is not a world in which there's free migration, but the world is not a world either in which migration is completely impossible. And so getting those numbers right, or getting reasonable estimates of the cost of moving will be key to get a reasonable estimate of the economic effects of sea level rise. Okay, and so so then in terms of the quantification, what about the sea level rise scenarios? What are we doing here? So we are using, we are using the probabilistic projections of sea level rise that were developed by Bob Kopp and others. So what they did is they took data from over 1,000 tide gauge sites around the world, and so they have estimates for each one of these 1,000 plus sites. They have estimates or projections of how the sea level will rise in these different locations between the year 2000 and the year 2200. And they have developed these probabilistic projections for 3 alternative pathways of future greenhouse gas concentrations. So as you may know, the IPCC has different they work with different scenarios of future stock of carbon in the atmosphere, and they call these different scenarios representative concentration pathways, or RCPs. The 4.5 is the middle of the road RCP, the business as usual, meaning if we keep doing what we're doing, that's the type of emissions we're going to see over the next 2 centuries. That's the 4.5. The 2.6 is sort of the optimistic scenario. If we were to implement the Paris agreements, we'd have a lot lower emissions. That would be 2.6. And then 8.5 would be the more pessimistic scenario, where the world grows in a very carbon intensive way, right? And so for each one of these 3 RCPs, they generate 10,000 Monte Carlo samples to calculate a probability distribution of sea level rise. Because obviously there's a lot of uncertainty, right? We don't know exactly, even for a given RCP, we are not 100% sure what's going to happen, say, with the ice sheets of Greenland and Antarctica. And so, depending on the sensitivity, say, of the melting of these ice sheets to an increase in temperature, we'll have more or we'll have less sea level rise. And that's why they do these Monte Carlo simulations, where they choose different parameter values for these different processes, and they come up with for each one of these RCPs, they come up with 10,000 different paths of global mean sea level rise. Okay, and then what we do is we take these 10,000 paths, we divide them in 40 equally sized 2.5 percentile bins, and then within each bin we take a random path we take a random path. And so we're essentially going to, for each RCP, we're going to do our exercise 40 times. So we're essentially taking 40 paths out of these 10,000 paths. Okay. Now they have data for 1,000 tide gauge sites. We're of course splitting up the world into 1 degree by 1 degree cells, and so we're going to have for each grid cell, we will take a distant weighted average of these different tide gauge sites to get a local estimate of sea level rise. That's kind of the approach. Once you have these estimates of sea level rise, there's one extra step, which is to say, okay, well, once I know how much the sea level will rise in these different places or in these different grid cells, what do I know then about the share of land that will be flooded? And for that, we need information on elevation. And so we use the coastal dam of Climate Central. They've estimated, they have estimates of local elevations that are based on NASA's SRTMs, the Shuttle Radar Topography Mission. And they manipulate those data to reduce vertical error because, of course, because of vegetation and because of population density, if you have, for example, high buildings, you may mismeasure elevation, right? So when you look from outer space and you try to measure the elevation of Miami, if everything is very tall buildings and you don't understand that you're looking at buildings rather than at the actual land, you will overestimate the elevation of Miami. I'm just saying that because this is an important issue in a lot in the previous data that we were using, because we went through different different steps here. We were using older data on elevation, and we were getting very odd results for Miami. And it turned out that these older data on elevation were severely overestimating the elevation of Miami, and it was mainly due to the fact that it was mismeasuring buildings, as if the buildings were the elevation of the land, right? And so because you're thinking about a sea level rise of just say 0.5 meters or 1 meter, even very tiny errors in elevation may have huge consequences on your estimate of land that will be flooded, right? So if I just look at buildings and the buildings are all I don't know, 20 meters high, and I overestimate the elevation by say 5 meters, then suddenly nothing will get flooded, right? If I have a projection of flooding by 1 meter. So getting the best, I'm hoping we're using, you'll have to tell me, I'm hoping that we're using the best available data. I understand that these data are continuously being improved, but I do understand that using high quality data here is very, very important, right? So to the extent that newer and better and higher quality data are continuously being generated and are coming out, well, we should be updating some of these things using the best available data. Okay, so anyway, so we combine sea level rise with data on elevation. The reference is the local high tide, and then what we get, and that's important, is for each grid cell and for each year, say starting in the year 2000 till the year 2200, for each single year, we get an estimate of the land available, and we get an estimate of how much land will be flooded, and then we can simulate the model forward for 200 years. Okay, so that's the nature of the exercise, and in the remaining 15 or 20 minutes, I'm just going to be showing you results. I'm just going to be showing you pictures. Okay, so here we go. So this is a picture of the global mean sea level rise. These are these 40 paths that I talked to you about, 40 out of the 10,000 Monte Carlo simulation. This is for RCP 4.5. Remember, RCP 4.5 is the middle of the road, business as usual emission scenario that the IPCC uses, right? And so what you can see here, if you look at the blue line, that is the mean. That's the mean sea level rise between now, say 2010, it starts 2010, all the way to 2200. By 2200, we're talking about maybe 1.2 meters. By 2100, we're talking maybe about 0.6 meters. The other thing you, of course, notice is that if you look at the red lines, these are these different paths that are taken out of the Monte Carlo simulations. There's, excuse me, there's a substantial amount of uncertainty here, right? So you could get sea level rise all the way up to almost 4 meters by 2200, or you could get sea level rise that is very, very little by 2200. So a lot of uncertainty here, and that's of course important to mention. Now we're getting to results that are generated by the model, right? By our economic model. So this is the loss in world real GDP under RCP 4.5, right? And so look at the red curve, right? Again, we're going from 2000 to 2200. There's a few things you can see here. One is, if you look at the y-axis, you say, well, these estimates are not really very large. We're talking about at the maximum maybe 0.4, 0.5% of world GDP. That's one observation. Well, of course, you have to realize that climate change is a much bigger phenomenon than just coastal flooding. So this is the cost of climate change at the level of the world GDP only due to coastal flooding. And of course, let's say 98% or 96% of world GDP isn't impacted, right? Because it's produced at places that are not at risk of flooding. Anyway, so that's one thing you notice. The other thing that's very interesting here is that it's actually non-monotone, right? So it goes up and then it goes back down. And so you could wonder if sea level keeps going up, shouldn't the economic costs in terms of GDP keep going up as well? I think that would be the right intuition to have. But the fact that this is actually going up and then going down, so that the costs are rising till about 2140, and then they start to sort of level off and go down, has to do with the fact that in this model, the economic geography of the world is continuously adapting and responding. So you have to sort of understand that, yes, certain clusters of economic activity are being destroyed, but people are moving to other places. Where they're moving to, they're adding to the economic activity of these other places. Maybe new cities, new clusters of economic activity are emerging elsewhere. These places will also be increasing their productivity. They will be innovating, etc. And so in that sense, nothing really tells you, let's say from the economic point of view, that these effects should be monotone, right? It may be non-monotone, and in fact, as you can see here, it's non-monotone. The other thing you of course also notice, those are the gray curves, is that again, if you do this for all 40 paths of global mean sea level rise, you'll have the costs can be a lot bigger, right? So if you say here that the cost is 0.4%, in a really bad scenario, the cost may be triple the size. In a really good outcome, the cost may be a lot smaller. So there's a lot of, again, a lot of uncertainty here. Let me skip a few slides here, not to okay, let me actually show you this too. You can, so the previous one is looking year by year, right? You can of course come up with one number if you want to, so you can calculate the present discounted value of all the future losses, right? And then you can say, from today's point of view, what is the present discounted value of all these future losses? Well, we come up with numbers that are around 0.2% of real GDP. So this is the number here, 0.19. If you take RCP 4.5, you get a loss of about 0.2. In a worse scenario, RCP 8.5, it goes up to 0.25. In a better scenario, it goes down to about 0.15. So this is kind of the range of losses we're looking at. Let me move on here. Sorry, this is moving a bit too quickly. Okay, so another thing you can look at is what about the world population that is displaced, the percentage of the world population that is displaced. That is, of course, monotone, right? Because more and more land gets flooded over time, and so more and more people will be displaced. We're talking about on average by 2200, maybe something around 1.3, 1.4% of the world population. Once again, lots of variation depending on exactly what happens to this global mean sea level rise. Okay. And so again, you can come up with some numbers here. As I said, in the RCP 4.5, you have about 1.5% people displaced by 2200. By 2050, about 2.2% people displaced. Okay, let me move on a little bit. So this is actually a very important graph. So let me spend a few minutes on that before I show you also some results for more localized results rather than talking about global effects. So one thing I emphasized in the beginning of my talk is that some of the more, I could call, naive estimates of the cost of sea level rise are estimates where they essentially simply calculate the GDP that is lost in places that become inundated. So, as I said, the part that they're missing when they make a calculation like that is, on the one hand, it doesn't take into account that GDP that's lost in one place will partly be compensated by GDP in another place, because the people who live there are going to move somewhere else, and wherever they move, they're going to start producing something as well. And secondly, they also miss all the possible dynamic effects, which is, certain clusters of economic activity in coastal areas may disappear, but probably new clusters of economic activity in other places will pop out. And so this is what you can see over here. If you look at the blue curve in this figure, these are our estimates. Okay, this is similar to the graph I showed you before, this hump-shaped graph. It shows you the real, it shows you the real GDP losses, right? And so again, it maxes out at about 0.4, 0.5% of GDP in the middle of the 23rd century. Oh, sorry, the 22nd century, it maxes out at about 0.4 if you look at the blue curve, and then it slowly goes down. Whereas the red curve is the naive model where we say the zero adaptation, right? Stuff gets flooded, that stuff is lost. Those losses is what I'm calculating, right? Instead of saying, well, again, some of these losses will be compensated because people move somewhere else and they start producing somewhere else. So if you wish, the red curve, which shows you by 2200 a loss of almost 4.5% of GDP, those are simply the losses in terms of economic activity that gets destroyed in coastal areas without taking into account the fact that it will be partly compensated by economic activity being generated or created elsewhere. And so that's the difference between the red curve and the blue curve. Then there's some other scenarios that are in between cases, but that's kind of, if you wish, the difference between the red and the blue is what you get or how you mitigate the overall losses by the fact that humans can respond by moving, even though moving is costly, right? I mean, if moving would be completely free, arguably the cost would be even lower. Okay, so here's sort of to finish up a few last slides. So you may get a little bit impression that the numbers I'm giving you are small numbers, right? I'm saying, okay, the loss in the present discounted value loss of real GDP for the global economy, 0.2% of GDP. You could say that's not very much, but of course that's a global average. The real issue in our view of climate change in general and of coastal flooding in particular is, of course, that these losses will be very, very unequally spread across the globe. So the fact that globally the numbers are relatively small says nothing about local, right? So locally, some of these costs may be extremely high. And so you get a little bit of a flavor when you look at this slide over here. These are the losses for every single grid cell, right? And so the red ones, for example, are losses of more than 10%. So you see, for example, the coastal areas of East Asia, you know, the coastal areas of China, you look at Bangladesh, you look at Vietnam, you look at Cambodia, you look at all those places, very, very large losses locally. The US Gulf Coast, southern Florida, parts of the Atlantic coast, parts of the Gulf Coast in Mexico, very, very large losses. Same thing for northwest Europe, Belgium, the Netherlands, etc. Very large losses. Much smaller losses, say on the Pacific coast. Of course, the elevations there are higher. Pacific coast of South America as well, much smaller losses. In Africa, the losses are relatively limited as well. In Australia, the losses are limited. But the point is that, and by the way, all these green areas are gaining a little bit. Right? Of course, it's very small, but and why are they gaining? Well, because economic activity is being pushed away from the coasts, and all these other places are actually experiencing small gains. They're small, but they're there, and that's why all these other places are green, right? And so the point is, yes, relatively small average losses, but locally these losses may actually be very, very substantial, right? And that's why the spatial analysis of climate change in general and of flooding in particular is very, very important to do, right? But at the same time, you need to be able to take into account all these global linkages, right? I think this type of analysis is more useful than saying I'm just going to hone in on southern Florida and completely ignore all the linkages of southern Florida with the rest of the world. Okay, as I said, you can then, so this was done at the level of grid cells. You can do it at the level of cities, you know, and then of course, you know, you look at places like Shanghai, very big losses. Bangkok, well, the loss shows up here as 167% loss. You can say, well, a loss can't be more than 100. Well, this is because it's expressed as how much bigger is say GDP under no flooding versus flooding. So it's a bit expressed in a different way. But the point is quite a bit of variation. Places like Bangkok, Ho Chi Minh City, Shanghai. Well, you've seen it on the previous map. These are places that are going to lose a lot. Others not that much. You look at, say, Barcelona, they will actually slightly gain. There's not a big issue there in the Mediterranean. You know, you look maybe at Buenos Aires. Yeah, a loss, but a very tiny loss. Well, why is that? Well, because that part of the world is not going to, on the one hand, not going to have such big mean sea level rise, and it may also have to do with the slightly higher elevation of, say, a place like Buenos Aires compared to Miami. So a very big variation in the losses. Okay, so let me, in the interest of time here, start concluding, there's a bunch of other things here, but let me kind of recap things and emphasize that our main contribution compared to previous assessments is that we allow for this dynamic adaptation through migration. And that means that existing clusters that are being destroyed by sea level rise and permanent inundation can partly be replaced by the emergence of new clusters of economic activity. And when ignoring this dynamic adaptation, real GDP losses increased to 4.5% in the year 2200, up from 0.11%, right? And so that's important. One thing that I also wanted to mention is that we are leaving out some important aspects. So for instance, I have said nothing about mitigation, and I haven't said anything about adaptation in terms of limiting sea level rise, right? So of course, humans can build seawalls to protect themselves. I mean, the Dutch are masters at that, right? So you can protect yourself. We're not looking at, we're sort of looking at what would happen, and we're quantifying the costs if we don't do any of that type of adaptation. So that's important to mention. The other thing that we are kind of interested in is, and this may be something to get some feedback on. So notice that we've taken this economic model and we're taking these global sea level rise data kind of exogenous to our model, right? A more comprehensive analysis would incorporate feedback between economic outcomes and flooding. What I mean by that is the following. Papers that have looked at the phenomenon of global warming, right, would say, okay, when the temperature goes up, that will affect economic activity. Say it will affect agricultural crop yields, right? So there's the climate affecting the economy, but then of course the economy, because it produces emissions, also affects the climate, right? And so there's a feedback. And so we could of course entertain here a more comprehensive model where you say there's sea level rise that affects economic activity, but economic activity, because it affects temperature and temperature affects sea level rise, you could build in a feedback loop where it's not just sea level rise affecting the economy, it's the economy affecting sea level rise. But in order to do that, we would need to have good estimates of how increases in temperature affect local sea level. If we had good estimates for that, we could very easily build in that feedback loop. So again, the point is, do we have good estimates for how say a 1 degree or a 2 degree increase in temperature, how does that affect the sea level in all these places around the globe? If we had good estimates on that, we could easily build in that feedback loop. And I think that would make for an even richer analysis, because at the end of the day, these things are of course caused by human activity. And so we would like to go beyond just saying the sea level affects the economy. We would also want to incorporate this idea that the economy affects the sea level. So I'm going to stop here, and I'd be interested to know if there's any questions. Let me yeah, go ahead.
Thank you, Klaus. That was a very interesting talk. I think first in the chat we have Vivian, and then I will open it up to any questions. Vivian, could you go ahead and unmute if you have to?
Yes. Yeah, I was just wanting to comment or perhaps ask, because I think you mentioned it at very near the end, but I thought that important things were left out. of the economic considerations, namely that when you would talk about adaptation, it seemed more like the economic activity would shift away from the coast, and that was the nature of the adaptation, as opposed to building coastal resiliency, by the various engineering or nature-based solutions that are commonly mentioned in that context. And the reality, it seems to me, is that the coastal areas are gaining population and activity in spite of what we know about sea level rise. It's not, maybe the local officials are taking it into consideration and making plans and what have you, but that doesn't seem to deter the plans to keep building more and more very near the coast.
Yeah, so this is a very interesting question. So let me respond in two ways. On your last point, you're actually quite right. People are indeed moving more and more to the coast. In fact, in our own economic model, when we simulate it forward, we actually find the same model generated effect. So people are increasingly in our model as well moving to the coast. And the reason is that the coasts are very attractive, at least in our model, right? The coasts are very attractive for a number of reasons. They're, of course, places with high amenity value. People like living close to water, but they're also high productivity places. Coastal cities are very well connected to the rest of the world and to the rest of the world economy. So coastal sea transportation or water transportation is much cheaper than land transportation. That's why if you say go to a country like China, it's not surprising that all the economic development is essentially happening on its eastern seaboard. You go to South America, all the economic development is essentially on the Atlantic coast of Brazil, the Atlantic coast of Argentina, etc. So coastal areas, for both economic reasons and for their amenity value, continue to be very, very attractive places for people to live. And so in that sense, I agree with you. What we have done, and as you point out, what we have done is a partial analysis. We're saying if we don't improve engineering structures, or if we don't improve, say, resiliency of the type that you have in mind, then this would be the cost globally, and this would be the cost locally. Once you have these cost estimates, you can compare those cost estimates to saying, well, what would the price be, for example, to build these engineering structures? So you could say, okay, the loss, if we don't do anything, the losses to Miami will be 6.5% of local GDP. What is the cost of protecting Miami by building engineering structures that protect the city? If those costs are if the price tag of that is much smaller than the 6.5%, well, then maybe you say there's a positive return here, and the cost benefit analysis tells me that it makes sense to protect some of these places. So I think that's the sense in which our numbers are useful as a kind of an input of a broader cost benefit analysis, I would say.
Okay, thank you very much. Next we have Jeff.
Hi, idea that there's a temperature dependence on sea level is often used just a pattern matching. So whatever the pattern of sea level rise is in the first 1 degree, you just multiply it by 5 for the next 5 degrees. And so you can get this temperature dependency, and that's largely done because most of the sea level rise at the moment is thermal expansion, and right. So you can put that component in just by saying the pattern will be.
Oh, I think you got muted for a second. Yeah. So what you're suggesting is, so that most of the sea level rise is because of thermal expansion. And so if we have good measures of how the local sea level in all these different places has been reacting in recent decades to small changes in temperature, then you sort of, in a way, take that pattern and sort of extrapolate it and use that as a way of having a local dependence of sea level rise on temperature. Is that?
Yes.
Yes, I understand. Yeah, I think that would be useful for us to do, I think. Thank you. Any other comments or thoughts?
Sorry, can you hear me?
Yes.
Oh, sorry. Yeah, my internet is a little on and off. I'm really sorry about that, guys. Does anyone have any questions? I have a question. Okay, I will ask. Jeff, you still have your hand up. I will check in a moment. So I was a bit interested in the mathematics or the physics of your model. In particular, I was hoping you could talk a bit more about the key variables that you've chosen and how the relationships are determined between them. So you mentioned earlier that perhaps key variables are things such as amenities and like the position between one grid cell and other key grid cells. I was just wondering where that theory comes from and how you chose what components were important and
Yes.
what empirical analysis you use to determine the relationships between those key variables.
Yeah, so this is part of a much more, say, comprehensive economic model. I was just sort of trying to summarize it in 2 slides, and so very briefly, the way these models work is, imagine you have, as I said, many different locations, and people have to decide where to live, right? And so on the one hand, they care about the productivity of a place, because the productivity of the place will be the key variable that affects local income. They will also care about whether they enjoy living in that place. So there's both the working and the living. So I may be willing to take a lower wage if a lower real wage if I live in a place that's very beautiful, for example, that I find very beautiful, right? And then the geographic position relative to everyone else also matters, because think about, so your wage matters, right? How much you like a place matters. That's the productivity and amenities. But the third thing that matters is how expensive are things. So if you live, say, as I said initially, if you live in the middle of nowhere, you're going to have to import lots of the stuff from very far away, and that will be expensive. So you'll be facing higher local prices if you live very far from everything. And so if you take those 3 things into account, I care about my dollar wage, I care about the prices of goods that I want to consume, and I also care about whether I like the place as a place to live, right? Those 3 things will at the end determine my well-being in a particular location, right? And so then you start off, say, with a distribution of people across space, and of course some locations people's well-being will be better than in other locations. So obviously, if, say, I compare an advanced economy to a much less advanced economy. In a much less advanced economy, maybe in sub-Saharan Africa, people's well-being is going to be lower than in an advanced place, I don't know, in America or in Western Europe, in Japan, what have you. And so people might have an incentive to move, but moving may be very costly, right? And so maybe they can't move, or there is some migration, but the migration is very slow in the direction of places that have higher well-being. And so essentially we start off we use data on population, on local GDP, and on other economic variables to kind of rationalize today's distribution of people and economic activity across space, right? And then you kind of simulate the model forward, and over time what can happen is, on the one hand, people can move. Again, the costs of migration tend to be very high, but there's some movement of people. When people move, things have to readjust. And in addition to people moving over time, you also have productivity increasing over time, and productivity increases based on, say, the size of the local market. If I'm in a location with relatively high productivity, with a large local market, I'm going to have higher incentives to innovate. And so some of these places will innovate more than others. And that as well will then cause readjustments, because the places that innovate more will attract more people, etc. But then there's also going to be a limit on that because of congestion, right? And so we have kind of an economic model that has equations for these different forces that I just highlighted. And then we have data, as I said, on population, on productivity. We have estimates on how expensive it is to move goods between any two cells, depending on whether it's a sea route, whether it's a land transportation, water transportation, depending on the road network, etc. And so we have these estimates, and then, as I said, we have some assumptions about how people move, how costly it is to move, and how firms innovate. And that allows us to then kind of simulate the model forward and see how the economy evolves. And the sea level rise simply just kind of eliminates certain pieces of land, forces people to move elsewhere.
Thank you. That's really interesting.
Yeah.
I would love to talk more about the economic model that you use and the assumptions that it's made, and how you determine the relationships between those factors.
Yes.
I'm really intrigued by the blue line. So a moment ago, you showed the blue line, which showed the economic percent change in GDP by.
This one here.
Sorry. Yeah, I'm intrigued by why it's declining after 2140.
Yeah. So
I believe that implies that the economic growth in the run with sea level rise is higher after 2120 than a run without sea level rise. I'm not sure why it would decline. If anything, I thought it would flatline after.
Yeah. So here, so all these curves over here are showing losses, right? And so what the blue line shows is that the losses are increasing over time, and at some point flatten out and start to decrease. In fact, this blue line here, or this blue curve, sorry, is identical to it's identical to this one here. These are the GDP losses, right, that are initially becoming larger and then smaller. Now, I agree that the non-monotonicity we also didn't expect, because sea level rise keeps increasing, right? That's clear from the previous picture right here. The sea level rise keeps going up. Then why don't the losses keep going up? And that's, of course, again, because of the economic model, where as certain clusters of economic activity get destroyed, that's partly compensated by new clusters emerging elsewhere. And I guess if that second force is strong enough, of course, that second force mitigates the losses of the first force. And if it's strong enough, maybe it ends up not being monotone, which is what we find over here. Because if you go to that curve if you look at the red, look at the blue is non-monotone. You look at the red one is of course monotone, meaning if you don't take into account that possible response of moving elsewhere and building stuff elsewhere, then the losses are monotonically increasing. That's the red one. The losses are monotonically increasing because the more sea level rise, the bigger the losses will be.
I also wanted to ask you what empirical analysis you used to estimate your adaptation parameters.
So what we did is, the main parameters. I mean, there's several things matter here, but I think one of the main things that's important is this cost of moving, right? The parameters that determine how easily is it or how difficult is it for people to move. And the way in which we estimate those parameters is we actually have data on the population distribution across the globe for different years. And so what we ended up doing is we took, say, the initial year, we simulated the model forward, right? And then we chose the migration cost parameter such that when I start in year 1 and simulate forward, say to year 10, that I match exactly the changes in population that I observe between year 1 and year 10, right? So we're kind of getting these migration costs from the data, meaning, to give a simple example, suppose you say Congo is a relatively poor place, relatively low well-being, in a model where migration is easy, you would expect a lot of people to move out. If in the data I notice that very few people are moving out, then I'm going to say it must be hard to out-migrate from Congo, right? And so it's that intuition that kind of justifies saying I'm using the actual change in population location by location, and I'm choosing the migration parameters such that the model matches exactly the changes in population that I observe in the data. So that's the main adaptation parameter. Then there's also, of course, the adaptation parameters in the sense that once people move to a place and these places become more dense, how does that affect incentives to innovate, etc. And there's relatively good estimates in the economic literature on that. So, for example, you could say if a city gains 10% more population, how much more productive will a city become? Right? For that, there's actually relatively good estimates in the economic literature. So that parameter value we get from other studies.
Thank you, Jeff. I'm really sorry. I believe you had your hand up. Do you have a question?
Yes. Yeah. So I presume that this is an agent-based programming of each population unit being an agent, and then you've got attractors and repellers in that. But if networking theory has been used in looking at migration, and it seems more that the attractors for migration are associated with how many people you know in the location you're going to, and I guess you could include that in how people perceive that it's an attractive place to be, but it ignores the networking side of the theory.
Yeah, I mean yes. I mean we don't explicitly have, yes, that's right. We don't really explicitly have networks in the model. What we do have is, of course, the idea that more dense places attract more people, right? But again, that's more of a, I agree, that's more of an individual decision. You know, I'd rather go to a place with lots of people, but that's because that place is more productive, right? Yes, and so some of it will indirectly show up, right? So for example, if you say there are, if you say there are many people from Mexico migrating to America because they know people in America, right? Maybe family members or something like that, that would show up indirectly in our estimates because it would show up as migration from Mexico to the US being relatively easy, right? So there would, it would in that sense show up indirectly, right? So if there's a lot of Mexicans living in the US, to the extent that that is a network and it makes it easier for Mexicans to move to the US, then that would show up in our model as it being easier for Mexicans to out-migrate. But yes, but otherwise I agree. We don't have explicitly. We have some of it implicitly in the model, but we don't have explicit networks. That would be interesting to look at.
Thanks.
Thanks, Jeff. Do we have any final questions? I'm sorry, we've gone a little bit over time this week. Silence. It's very quiet. Okie doke. I was just going to say thanks again ever so much, Klaus. Thanks everyone for joining us. I hope you have a great rest of the day, and hopefully we have you back on in the future, Klaus.
Yeah. Well, thank you all. I mean, as I said, as an economist, this was a privilege to present to all of you, and thanks for all your comments and responses. Look forward to meeting you again. Thank you.
Thanks, everyone.